We continue Chapter 8, Lesson 1 with Example 2. And Example 2 says use a ruler and protractor to draw an arrow diagram for each quantity described. Include a scale on each diagram. Okay, so letter A, we are going to draw vector T, which is 10 miles per hour at a bearing of 25 degrees. Okay, first thing I'm going to do is take a protractor and I'm going to draw a coordinate plane, nice and neat. So here and here. Now our vectors are going to be drawn in standard position, and T is going to be 10 miles per hour at a bearing of 25 degrees. Okay. Now the first thing I'm going to do is focus on the bearing of 25 degrees. Whenever it says bearing, this represents a true bearing, which means it's going to be 25 degrees clockwise from north. So I am going to take my protractor, and where the window is, I'm going to line that up with the origin. Okay. Notice north is at 0 degrees if I go all the way to the top. So I'm going to move to the right until I find 25 degrees, and I'm going to make a dot at 25 degrees. Okay. Now next, I need to draw a vector representative 10 miles per hour. Now when I look at my ruler, see if I have one that's not so, oh, this one's a little better. Okay, I'm gonna use the centimeter side. And what I might do is maybe make 1 centimeter represent 5 miles per hour. Okay, that's my scale. Okay, and I can make my scale whatever I want it to be, but given the space, I'm gonna let 1 centimeter equal 5 miles per hour. So what I'm gonna do is I'm gonna line up 0 with the origin and take my ruler and line it up with the dot that was 25 degrees. And I'm going to draw a vector that is 2 centimeters long. Oops, I went past 2. Let's see, 2 was right here. I'm gonna erase. So it's exactly 2 centimeters long. And at the end of my vector, I draw an arrow. Okay. Now, a couple things I need to mark. Okay, I need to mark my angle. So from north to my vector was, remember, true bearing should be marked with 3 numbers. So 0 to 5, so 25 degrees. And my vector is T, that equals 2 centimeters. So now I have a vector, so if I take 2 times 5, that's 10, that's representative of 10 miles per hour at a bearing of 25 degrees. Okay, I would like for you to pause the video, attempt letter B, and when you're ready, hit play. Okay, so letter B, we have 25 meters per second at a bearing of 70 degrees south of west. So first thing I'm going to do is draw my coordinate plane, but I'm being mindful that south is below the x-axis and west is to the left of the y-axis. Okay, so here's my coordinate plane. And I know that this is north, east, south, and west. Okay. I want 25 meters per second at a bearing of 70 degrees south of, south 70 degrees west. So it means I start south and I'm gonna go 70 degrees in the westerly direction. So again, I'm gonna put the window of the protractor on the origin, line everything up. So south is at 0 degrees. South is at 0 degrees. I'm going to follow this until I hit 70, and I'm going to make a dot at 70 degrees. Okay. Again, I need to make a scale. Let's see, 25 meters. Maybe I'll use 1 centimeter equals 5 meters per second again. That means I need to draw a vector that is 5 centimeters long. So I'm just going to put my 5, I'll start at 7. So if I have 7 at the origin, 5 centimeters would take me out to 2. Line it up with my 70-degree mark. Okay, and I have a 5 centimeter vector. I know from the south to the west, this is 70 degrees. This is vector z, and vector z is 5 centimeters. So if I take 5 centimeters, and each is 5 meters per second, 5 times 5 would make that 25. Very good. Now I'm going to give you an opportunity to read about operation with vectors. Okay, so take a moment, pause the video, and just read what this has to say. And when you're ready, hit play. So parallel vectors have the same or opposite direction, but not necessarily the same magnitude. So again, parallel means they will not cross. So if I look at the picture, it looks like all of the vectors are parallel for the example of vector D. So I can say that vector A is parallel to B, is parallel to C, is parallel to E, is parallel to F. Equivalent vectors have the same magnitude and direction. So if I look at all the vectors, it appears that A and C are the same length, and A and C also go in the same direction. So vector A would be equal to vector C. Okay, opposite vectors have the same magnitude or length, but not the same direction. Their directions are exactly opposite each other. So if you look, notice vector A, the arrow points up and to the right, well, vector E points down and to the left, but they appear to be the same length. So I would say that vector A and vector E are opposite vectors. Okay, also, looks like vector C and vector E are opposite vectors. Okay, and we're going to wrap up example 2 with resultant vectors. So when 2 or more vectors are added, the sum is a single vector. Geometrically, the resultant can be found using the triangle method or the pyramid method. I typically prefer to use the triangle method, which is called the tip to tail. So say, for example, I have vector A and I have vector B. Okay, and I want to find A plus B. The triangle method is also called the tip to tail method. And what happens is we kind of just take these vectors and put them together so that they are touching. So vector A would come first. So here's vector A. And I would move vector B so that the tail of B hits the tip of A, and I would draw vector B. Okay. So what's happening is vector A starts down here and vector B ends up here. The resultant vector is the sum of A and B. And the resultant vector is the vector that starts where A begins and ends where B ends. Okay, we call this R, the resultant vector, and this is equal to the sum of vectors A plus vector b. This is called the triangle method. Also known as the tip to tail method. I'm not sure if you saw any of that. Again, I'm just going to double check. So here we have vector A, and then I take vector B, and it begins where A ends. And so the resultant, or the sum of the two vectors, goes from the beginning of A to the end of B. This is the end of example 2.